All right, we're now transitioning over to Chapter 12 material. Chapter 12 is on matrices. Now, the idea of a matrix, was around a lot longer than the actual movie The Matrix, and it's maybe not what you think. The concept behind it is very simple. It's data entry. Pretty much whether you believe it or not, we see matrices all the time. Charts, graphs, even Microsoft Excel. So all these examples can be expressed through matrices, but there's already so much that we can learn about them. But right now, I want to start with the most basic stuff. Let me go ahead and cross this out because we actually don't know a lot about what a matrix is. Yeah. So we don't know what a matrix is, but we can go ahead and talk about the different parts of it too. So a matrix is a rectangular array of variables and constants in horizontal rows and vertical columns. Each object in a matrix is called an element. So it's really important that we remember this right here and this right here. So it can be very easy to confuse rows and columns. But here's how you remember. Look at the letter R in rows. Look at the letter R in right. So rows go from left to right. Columns do not. They go up and down. A matrix is usually given by a capital letter, where each element is being represented by its lowercase counterpart. When we describe an element in the matrix, we use the lowercase version of the uppercase letter, and we also denote which row and column that element is located. So here's an example. I have a capital A defining this matrix, 1, 2, 3, 4, 5, 6. Okay. So since A is the matrix, lowercase a is going to be described for every element in that matrix. So again, we want to recognize the row and column of each element. So if I wanted to find A1, 3. So the 1 tells me the row, the 3 tells me the column. So if I look here, if I look in the first row, this is the first row here, row 1, row 2. Column 1, column 2, column 3. So row 1 here, element 3, column 3, 1, 2, 3. So that's this element right here. So it's 3 because 3 is found in the first row and third column of A. All right. If I wanted to find, let's say I wanted to find A2, 2. That's the second row, second column. So second row, second column. That's this number right here, 5. Okay. So when we're describing elements, right, the lowercase a is it represents the bigger case a's elements, or just whatever lowercase, whichever uppercase letter you use to name a matrix, you use its lowercase version for each element, and then you find, and whatever number that you're looking at, you're looking for the row and the column, and those are the two numbers that are involved in there. Okay, so. We also talk about, we don't just also use matrices, or we also we also don't just describe a matrix by its elements. We can also describe it by its dimensions. Okay, so for example, in letter A, there's 2 rows, 1, 2, 3 columns. So because there are 2 rows and 3 columns, remember this goes first and this goes second. Rows always come first. Columns always come second. That makes this a 2 by 3 matrix. Okay. All right. So let's say I wanted to switch this around. Let's say I want to let A. I'm going to do this off to the side here. Let's say I want A. Let's say I want A to be this matrix. 1, 2, 3, 4, 5, 6. Okay, and let's say I wanted to find A3, 1. That's third row, first column. 1, 2, 3, 1. Also, it has 1, 2, 3 rows and 2 columns. So A would be a 3 by 2 matrix. Okay. Now there are different types of matrices depending on how they're formed, what they look like. Okay. Sometimes you have matrices with only one row. Sometimes you have matrices that only have one column. Sometimes you have matrices with, it's all the same number. Sometimes you have matrices with consecutive numbers, what have you. I'm going to go ahead and list the different types of matrices. So here's the first one. A matrix that has only one row and no columns is called a row matrix. And technically, we don't even need that. You don't even need this because obviously it's going to have columns if it has a row. But what stands out for the row matrix is that it just has one row. Likewise, a matrix that has only one column is called a column matrix. All right. Now, what if you have the same number of rows that you do columns? If a matrix has the same number of rows and columns, it's called a square matrix. So like 1 by 1, 2 by 2, 3 by 3. Those are the kind of things are square. The number of rows have to match the number of columns. So speaking of square matrices, if an n by n matrix, and that could be any dimensions, it could be 1 by 1, 2 by 2, 3 by 3, 4 by 4. If the n by n matrix has only ones in its diagonal from upper left to lower right and zeros in each other element, it's called the identity matrix. So early on in the year, we talked about the additive and multiplicative identities and inverses. Well, matrices also have identities and inverses too. I'm about to show you an example of what the identity matrix is. And our last type, a matrix in which every element is called 0, is called a zero matrix. Now the difference, you'll see in a second. So those are the 5 types of matrices: row matrix, column matrix, square matrix, identity matrix, and zero matrix. So if I look at here, for example, letter A has only one row. That's a row matrix. Okay, actually, zoom in here so you can see. Then we have B, which you have one column. That's a column matrix. Here I have 2 rows, 2 columns. This is a 2 by 2. That's a square matrix. And here, every element in this matrix, this is a square matrix, but every element in this matrix is 0. So this is the zero matrix. The zero matrix could be any size. It doesn't have to be a square matrix or not. It can be 1 by 3, it can be 7 by 5, it can be 2 by 2. And then, of course, here, so this is the identity matrix. This is a 3 by 3 identity matrix. So again, the identity matrix also can come in different sizes. And what makes it the identity matrix is this right here. This that diagonal of ones from the upper left-hand corner to the lower right, and everything else is 0. Now, another thing I want to mention is the zero matrix. The zero matrix usually isn't given by a capital letter. It's usually given by just a big 0. So that's the only exception to the rule on naming matrices, if it's a zero matrix. Okay. Now, so now that we know a little bit about basic stuff on matrices, now we can go ahead and talk about operations on matrices. So there are two operations there are 2 operations on matrices that are actually very similar to systems of equations that we just talked about. So remember, for systems of equations, we can change the order of any of the equations. We can add or subtract equations together, and we can also multiply by a non-zero real number. So in a similar way, we can do the same thing with matrices. We can add or subtract matrices to each other, and we can also multiply a matrix by any real number, which is usually called a scalar. Okay, and eventually we'll get to actually matrix multiplication in just a second. But right now, I just want to focus on addition, subtraction, and scalar multiplication. All right, so let's go down here. So here I have these 2 matrices. So let's say A is 1, 2, 3, 4, B is 5, 6, 7, and 8. Now, the only way that we can add or subtract matrices is if they have the same dimensions. See how this is a 2 by 2 and this is a 2 by 2? That's the only way that we can add them together. If I got rid of this bottom row right here, I can't add them together. They have to have the same dimensions. Now, when we add matrices, or even when we subtract matrices, you take one element here, you take each element, and you add or subtract its partner in the same position as that partner. So, for example, if I'm adding, then I have to add 1 plus 5. I have to add 2 plus 6. I have to add 3 plus 7, and then 4 plus 8. And same thing for subtraction, right? So if I do that here, 1 plus 5 is 6, 2 plus 6 is 8, 3 plus 7 is 10, 4 plus 8 is 12. And then same thing for subtraction. I have to subtract 5 minus 1, 6 minus 2, 7 minus 3, 8 minus 4. Now, for scalar multiplication, all you're doing is you're pretty much taking this non-zero real number and you're distributing it to every element in that matrix. Okay? So let me give you an example. Let's say I take 1, 2, 3, 4, and let's say I want to multiply it by 7. Then, that's 7 times 1, 7 times 2, 7 times 3, 7 times 4, which is 7, 14, 21, and 28. So with scalar multiplication, you have to take that scalar and distribute it to every element in that matrix. Okay? So again, in order to add and subtract, both matrices must have the same dimensions. Okay? And of course, when we do scalar multiplication, we want to distribute that scalar to every element. Okay. Now, also, like real numbers, matrices also have properties. So at the beginning of the year, we talked about properties of real numbers. Well, matrices also have properties too. So, for example, we have the closure property, and that's just for addition. We'll get into why multiplication doesn't exactly work. Okay. So for A plus B, so A, B, and C can be whatever dimensions that they have to be. If I can add them together, then that sum is also going to be an n by n matrix. So let's say I have a 2 by 1 matrix, and I add it to a 2 by 1 matrix. Then that sum is also going to be a 2 by 1 matrix. Okay. Also, like real numbers, matrices are commutative and associative, meaning that it does not matter the order with which we add them. Okay. We can add them in any order that we want. Then you have what's called distributive properties. So there's two different ones, but they pretty much mean the same thing. You have a left scalar distributive property and a right scalar distributive property. All that does is it takes the scalar and distributes it to each matrix. It takes it and distributes it to each matrix. It ends up being the same thing. It just depends on if you're distributing it to the right. If your scalar's on the left, it's left scalar. If your scalar's on the right, it's right scalar. Right. So you distribute the scalar into each matrix, and of course, for scalar multiplication, you distribute the scalar into each element. Okay. And then also, just like real numbers have an identity and an inverse, so do matrices for addition. There exists an n by n zero matrix such that if I add any matrix to it, I get itself. Okay. There's also a unique n by n matrix, negative a, such that if I add a to its opposite, negative a, then I get 0. Okay? So again, just like real numbers have these properties, matrices also has some of the same properties. Okay? The only other thing I want to cover is equality between matrices. How do I know that two matrices are equal? Well, they're equal if and only if each element in one matrix is equal to the corresponding elements in the other matrices. For example, I have a matrix A that's 2 by 2 with these 4 elements. If these two are to be equal, if A is equal to B, then this element here has to be equal to this. This element has to be equal to this. This element has to be equal to this. And this element has to be equal to this. So obviously, in this example, if A and B are in order for A and B to be equal, in order for A and B to be equal, that means that these two have to match, which they do. These two have to match. These two have to match. And these two have to match. Okay? But also, let's look at just another example. We're going to let A be the same thing. 1, 2, 3, 4. And we're going to let B be 1, x plus 2, 3, 4. So if these two are equal, obviously 1 is equal to 1, 3 is equal to 3, 4 is equal to 4. But this 2 has to be equal to x plus 2. So what's x going to be? What's x going to be? Let's find out. Subtract 2 on both sides. X is equal to 0. So that has to be 0. That x has to be 0 in order for those two to be equal. We can also write matrices like equations. So for example, we have what's called a matrix equation. So a matrix equation is one where the variable itself is a matrix. These type of equations can be solved using basic matrix operations. So if I have A, and A is equal to just 1, 2, 3, 4, and let's say B is equal to 4, 5, 6, 7. Okay, and let's say that I'm trying to solve this. AX is equal to B. Actually, hold on. Let me erase this. I got a better one. Let's say I want to take A plus X is equal to B, and I want to solve for X. Well, in order to do that, I have to subtract A on both sides. Okay, that means that X has to be equal to B minus A. Well, what's B minus A? That's 4, 5, 6, 7 minus 1, 2, 3, 4. All right, so we just do our basic subtraction. 4 minus 1 is 3. 5 minus 2 is 3. 6 minus 3 is 3. 4 minus 3, 7 minus 4 is also 3. So there's my solution right here. So again, with matrix equations, you're still isolating the variable, except this time the terms that you're moving around are actual matrices themselves.